Hello, I am a mechanical design engineer employed by Hy-Tek Manufacturing in Sugar Grove, Illinois. Through the Department of Defense Small Business Innovative Research Program, the United States Navy solicited interested small businesses to design and develop a replacement helicopter bay door seal for its Arleigh-Burke-class DDG destroyer. The objective of this development program was to design a replacement helicopter bay door seal using chemical-resistant elastomer materials that can provide greater reliability and in-service longevity than the currently deployed door seal. To satisfy these requirements, Hy-Tek invented the rolling door seal, or RDS, which is comprised of a hollow elastomer boot that is designed to roll into place and seal the helicopter bay when the door is closed. Once compressed beneath the fully closed 10,000-pound helicopter bay door, the elastically deformed boot forms a wide and liquid-tight seal along the ship deck plate. The engineered RDS boot geometry eliminates seal damage and failure typically caused by acute angle bending stress, while the high-strength elastomer from which the RDS is fabricated provides excellent resistance to chemical exposure and abrasion wear. During Phase 2 testing and evaluation, RDS prototypes were subjected to more than 20,000 simulated helicopter bay door opening and closing cycles without exhibiting significant wear or failure. When adopted for use on Navy's DDG destroyers, RDS technology will significantly extend the mean time before helicopter bay door failure, and therein significantly reduce DDG helicopter bay door seal replacement burdens and costs. Hy-Tek Manufacturing was founded in 1984 and has been a participant in the SBIR program since 2003. With core competency and experience in mechanical, chemical, electrical, and manufacturing engineering, HMC has been awarded 18 Phase 1 and 11 Phase 2 DoD SBIR awards. HMC facilities consist of an engineering research workspace of approximately 15,000 square feet and 43,000 square feet of manufacturing workspace. In addition to its engineering staff, HMC also employs 45 highly skilled manufacturing professionals who perform in-house mass production of custom-engineered products for the agriculture, mining, construction, and defense industries. An example of HMC's SBIR Phase 3 success is the high-load roller bearing, or HLRB, that is currently manufactured in-house by HMC and deployed on the helicopter hangar bay doors of Navy's Arleigh-Burke-class DDG-51 destroyer. The Navy's objective under this Phase 1 and 2 SBIR funding was replacing currently deployed DDG helicopter bay door seals with an engineered door seal capable of withstanding the deformation stress of repeated door opening and closing cycles without exhibiting rapid degradation, seal material damage, and failure. The replacement door seal must exhibit exposure resistance to fuels, hydraulic oils, lubricants, firefighting foam, salt water, and a wide range of operating temperatures. That door seal must also operate for a minimum of 4,800 helo-bay door open-close cycles without failure. The Navy's investment in this development project stemmed from predictable and frequent failure of the existing DDG helicopter bay door seal due to the material damage caused when the seal is deformed through an acute bending radius as the door is closed. The limited in-service longevity of that door seal is therefore not just a costly logistics burden for the Navy, but also a significant hazard to proper aircraft operation, flight crew safety, and overall fleet readiness. The DDG destroyer helicopter bay door seal, currently deployed by the U.S. Navy, exhibits unsatisfactory in-service longevity because of material failure caused by large bending stresses that exceed the yield strength of the monolithic-shaped seal. As the helicopter bay door is closed, the rectangular monolith seal is forced to bend through an angle that approaches 90 degrees. As the photographs on this slide illustrate, that sharp bending angle stress exceeding the material's yield strength causes the seal to tear away from its mounting assembly. Once that material is torn, the integrity of the liquid seal is compromised and the possibility of fuel, chemicals, and salt water contacting and damaging aircraft stored in the helicopter bay is increased. The engineered design of the RDS, along with the chemical-resistant elastomer material from which it is fabricated, eliminates these capability gaps. HMC's RDS is comprised of a hollow elastomer boot having a geometry that allows it to roll into place beneath the helo-bay door. Once in place, the RDS forms a wide and dependable liquid seal without the application of excessive compression or bending stress. This performance is made possible by the beneficial deformation behavior of the RDS boot when subjected to moderate bending and compression stress. RDS was designed so that it is easily installed on the helicopter bay door using current mounting hardware and without the need for door modifications or special tools. Phase 2 testing of incrementally optimized RDS prototypes validated that it can readily exceed U.S. Navy's performance goal of 4,800 helicopter bay door open-close cycles without failure or liquid penetration. The photographs at the right of slide 5 shows a prototype RDS fabricated of thermoplastic polyurethane installed on a helicopter bay door seal mounting assembly. As illustrated in the top photograph, the geometrically engineered hollow boot comprises the bulk of the operable RDS water seal. That hollow boot is designed to limit the magnitude of compressive and bending forces exerted on the RDS during door opening and closing. As illustrated in the bottom photograph, once the boot is in place beneath the closed door, the large front bulb of the boot rolls from the front side of the mounting assembly to the rear, therein forming a wide and operable liquid seal at the bottom of the helicopter bay door. The wide liquid seal accommodates large and variable seal-to-deck gap distances and is formed without the application of bending or compressive stresses that exceed the yield strength of the RDS elastomer. The USOR 60A nitrile elastomer from which the RDS is fabricated was thoroughly tested during Phase 2 work and was proven capable of satisfying U.S. Navy's exposure resistance requirements during prolonged contact with fuel, hydraulic oil, solvents, firefighting foam, and lubricants. HMC's matured Phase 2 RDS prototype was subjected to more than 10,000 simulated door open-close cycles atop deck plate surfaces of various roughness without significant damage or failure of the liquid seal. Phase 2 testing also validated that the RDS boot can be successfully used to seal both the RAS track and helicopter bay door corners. HMC's Phase 1 and Phase 2 RDS development was conducted using a well-organized engineering design, testing, and optimization plan that included critical development milestones. HMC engineers performed this plan in a chronological fashion that enabled follow-on RDS design optimization only after each previous milestone had been achieved. HMC first studied and analyzed the predominant failure modes of the current DDG helicopter bay door seal, as well as door seal material and performance requirements delineated by U.S. Navy. HMC studied and evaluated the condition under which the door seal must operate to identify additional root causes of rapid deterioration and failure. Based on these studies, HMC produced several promising Phase 1 RDS design concepts that showed promise in alleviating the large mechanical stresses that cause rapid seal failure. HMC also researched and identified promising elastomers for RDS boot prototype production and testing. Initial RDS design variant prototypes were 3D print fabricated for the purpose of conducting extensive testing, evaluation, and incremental optimization. RDS elastomer candidates were selected and evaluated according to U.S. Navy's exposure resistance requirements, with the most promising elastomer candidates selected for follow-on testing, evaluation, and down selection. During the Phase 1 option period, the most promising RDS boot designs were down-selected for follow-on RDS prototype testing, evaluation, and incremental optimization. As Slide 7 illustrates, during Phase 2 RDS development, HMC again utilized a well-organized and chronological work plan and milestone roadmap. This plan included design and development of RDS connector joints for the RAS track and door corners, as well as the development of tooling with which to efficiently fabricate 20-foot lengths of the RDS boot. That RDS prototype, fabricated of USOR 60A nitrile, passed all chemical and environmental exposure testing and exhibited no damage or liquid seal failure when subjected to 16,000 continuous simulated open-close cycles. To address the RAS track and door corners, HMC designed and fabricated prototype RDS joints for sealing those areas while concurrently designing a second test apparatus that replicated the RAS track and door corners. HMC's Phase 2 option period work plan included completing fabrication of the Phase 2 RDS test apparatus containing the RAS track and door corners and fabricating a newly optimized RDS prototype. HMC used its enhanced Phase 2 RDS test apparatus to subject the optimized RDS prototype to repeated door cycling atop the flat deck plate and simulated RAS track and door corners. While HMC developed RDS boot joints specifically for that purpose, Phase 2 option period cyclic testing validated that a continuous length of RDS boot is capable of properly sealing those areas without the need for splicing together sections of RDS boot. HMC will conduct water spray testing to validate that performance and design procedures to facilitate logistically simple RDS installation on board ship. Finally, HMC will collaborate with U.S. Navy to schedule RDS prototype installation on a DDG destroyer helicopter bay door and conduct comprehensive testing and performance evaluation. Development of the RDS focused on optimizing both its liquid sealing capability and in-service longevity. The geometry of the RDS boot and the USOR 60A nitrile elastomer from which it is fabricated were both designed and down-selected for that purpose. USOR 60A nitrile elastomer was selected for RDS prototype fabrication because it delivers excellent chemical and environmental exposure resistance properties as well as excellent yield strength, elastic deformation, and compression set performance. During Phase 2 testing, the engineered RDS boot geometry produced a wide, reliable, and repeatable high-strength liquid seal. Comparing the design of the RDS described herein and that of the existing DDG helicopter bay door seal highlights the reasons why RDS delivers superior performance and longevity. These include: 1. RDS boot geometry eliminates the need to exert damaging compressive and bending stresses on the structure to form a liquid-tight seal, while the existing door seal rapidly fails when subjected to bending stresses beyond its yield strength. 2. RDS forms a wide compression seal created by moderate elastic deformation forces, while the existing seal forms a narrow seal created by large bending forces that exceed the seal's yield strength. 3. It will provide at least 2 orders of magnitude greater service longevity. That longevity will drastically reduce Navy seal procurement costs and the cost of frequent seal maintenance and replacement logistics. HMC calculates that RDS deployment across the DDG fleet will reduce Navy's helicopter bay door seal costs by a factor of 10 or more, resulting in an excellent return on investment. And 4, the innovative RDS design and its proven performance and longevity make it suitable for use in a wide variety of other military and commercial liquid seal applications. The current slide shows the path for RDS transition delineated into chronological steps. The first step is completion of incremental Phase 2 RDS design optimization and thorough material and performance testing performed by HMC and the U.S. Navy. This step will include conducting final RDS material exposure resistance testing, RAS track and door corner liquid sealing performance, and overall RDS performance validation when installed on a U.S. Navy DDG destroyer helicopter bay door. Once RDS testing and performance validation has been successfully completed in these environments, RDS will be a TRL-7 product. At that point, HMC will complete the design of the final RDS extrusion mold and implement its plan to develop efficient and cost-effective RDS mass fabrication processes. HMC's final transition step will be to design and develop an RDS replacement kit and shipboard installation procedures that are rapid and logistically simple to perform. HMC is currently on schedule to complete these TRL-7 transition tasks on or before the end of Phase 2. As shown in Slide 10, HMC has completed a thorough study of the military and commercial markets for RDS. The most obvious and immediate market for RDS is of course the U.S. Navy DDG destroyer fleet currently fitted with the existing helicopter bay door seal. Follow-on RDS commercialization and marketing efforts will focus on commercial marine vessel applications that exhibit similar liquid seal challenges. These include liquid-tight seals on private yachts, cruise ships, ferries, and large cargo transport ships, among others. Non-marine vessel applications for RDS technology include liquid-tight doors for industrial plants and chemical factories, flood door seals, irrigation system seals, and liquid-tight seals used in the agricultural, mining, and construction industries. HMC's approach to successful RDS marketing and sales includes: 1. Identifying the performance, capability, and longevity gaps between existing liquid seals used in each sector and that of the RDS. 2. Highlighting superior RDS performance, reliability, and longevity versus that of existing liquid seals. 3. Tying those performance and longevity metrics to reduced liquid seal acquisition and replacement costs. And 4. Leverage improved RDS performance, longevity, and low cost of ownership to sell RDS based on exceptional return on investment. As illustrated in Slide 11, the most critical RDS stakeholders are those that will immediately benefit from HMC's successful RDS Phase 2 development efforts. These RDS transition stakeholders are separated into 3 categories. 1. Those involved in the purchase, use, and manufacture of military marine vessels, including all military branches and all military vessel OEMs. 2. Those involved in the purchase, use, and manufacture of all commercial marine vessels. And 3. Those having non-marine vessel liquid-tight seal applications that are critical for safe and successful operations. HMC understands that the foundation for successful commercialization of RDS into the private sector will be successful completion of its SBIR-funded Phase 2 RDS development work and development of those application-specific RDS design variants. Those wishing to learn more about RDS design features, performance, and cost benefits can contact either Mr. John Jude or Mr. John Bastian of Hy-Tek Manufacturing using email addresses and phone numbers provided on Slide 12. Please feel free to visit HMC's corporate website at www.hytekmfg.com. Thank you.